Their digging mechanism is starting to raise up.
Both robots working or moving now.
So Colorado Boulder put their auger in the middle of the robot. You'll see some of the teams put it out front. Some of them put it in the middle. There's so many design decisions that all these teams can make, and there are trade-offs for every single one. Colorado Boulder is already over into the digging area, just like that, lickety-split, less than 30 seconds. And York College is making their way very nicely also. This is a close-up of Colorado Boulder. You can see their auger system moving downward, and you can see it kicking up some dust.
And again, in the control room, they can't see as clear a picture as we're having out of here.
That's true.
But they do have access if they want it, but they get penalized for that. Is that correct?
They have access to 2 different camera views, but they're low-quality camera views. The camera views on the bottom of the screen right now are the camera views that those students can see if they choose to do so. So on the left, Colorado Boulder, we did see some digging happen. Now it's hard to see, it's hard to tell if something's moving or not at this point. Oh, definitely moving. So the idea is that the auger on the Colorado Boulder side will auger up the material all the way up out the top, and then it will spill out onto the onboard dump bed, which is basically just like a truck bed or like a dump truck bed, and then that whole bed actually lifts up in order to dump that material out. Now the CUNY team is made it over to the digging area, but they haven't started digging yet. It looks like they're rotating the robot.
They're both manual, correct?
It's hard to tell on the left side if the students are controlling that robot or not, but you can see a student on the CUNY side definitely controlling a joystick or a gamepad. My first guess, by looking at the Colorado Boulder students, my first guess is that they are not controlling that robot. So these students that have decided to go with an autonomous system, during their run, if they perform a completely autonomous run for the entire 10 minutes, they'll get a lot of extra bonus points. And so that's why you'll see that teams don't grab the joystick right away. They're gonna wait it out as long as possible before they give up. Because if they can deposit just a little bit autonomously in a fully autonomous run, that gives them a huge advantage over other teams that were not able to do that.
Explain for the folks in the audience who probably are not aware of all the different criteria that the judges consider for points. Many, many variables, correct?
There's a lot of variables. There's the weight of the robot. There's the communication that the robot uses between the robot and the control center. There is the power that is used on board the robot is taken into consideration. And also, obviously, how many of these rocks, how much of the rocks that these robots were able to collect and deposit back at the lander. So all of these variables had to be taken into account during the design of these robots for all of these teams.
In keeping in mind with what we discussed about the cost of putting something into space, the more you can do with less is essentially the key.
Yes, it's definitely a trade-off. The more complex you make your robot, the larger it ends up being, and the heavier it ends up weighing. So everything is a trade-off in real NASA missions and in this competition. We've tried to make this competition as real as possible for these teams. There we see the digger coming out of the hopper. It's definitely a
backhoe.
A backhoe.
Yep.
The CUNY robot, actually both of these robots appear to be having a few issues with mobility. because moving around on this crushed volcanic rock is not easy for any of these robots. There's a lot of trade-offs there just in your wheels. You've got your wheel diameter, you've got your wheel width, you've got treads on your wheels. There's a lot of decisions. What material do you make your wheels out of?
This is very, very fine dust.
Yes.
Extremely fine. And you were mentioning yesterday, I think, about it taking on a fluid, dynamics of fluid.
This volcanic dust can actually, take on a hard, packed form, but as soon as you jostle it, as soon as you start driving in it and start mixing it up, it can actually fluidize, and your robot can actually sink down into it if you're not careful about how you drive on it. And some of the students are finding this out the hard way. So it's exciting to see the York College robot extending its digging bucket. We do have 3 minutes and 40 seconds remaining, so it's going to be exciting to see what progress this York robot, now that it's finally into digging position, how much it's going to be able to dig in this 3.5 minutes that remain. Sometimes these robots end up being very fast and very agile. That can work for you time-wise. It can work against you sometimes, depending on how, if it makes you dig in because, you're not taking things carefully and slowly. So everything about the design of these robots is a trade-off that the students have to learn, sometimes the hard way.
Looks like we're digging a little deeper there.
If they go back and dig in the same exact spot over and over and over, then they'll get deeper each time, increasing the possibility that they'll be able to get hold of some of those rocks that we've buried under the topsoil.
And again, no points for the topsoil.
No points at all. No points at all are awarded for the topsoil. It is great experience, though, and they can take that experience into their second run.
That's working well, though.
It is. It's definitely digging. The Colorado Boulder robot hasn't moved in a while, so I'm guessing the Colorado students are troubleshooting to see what's going on. There you can see the Colorado Boulder students in the control room on the left side, the York College student on the right side controlling that robot manually. It's digging nice and deep. That's exciting to see.
You get that right angle so that it doesn't all come out prematurely and miss the vehicle.
Now that CUNY robot only has 1 minute and 12 seconds to come back and deposit its load. So it's possible that that student decided best to just dump that last bucket full and come back. Now it did take a while for this CUNY robot to turn into that position based on the wheels digging into the loose Regulus simulant. So 45 seconds, that's not a lot of time to get all the way back, turned the right direction and get all the way back to the lander. I'm afraid it looks like time is getting really short for this team. But still really good experience for these students to actually get this digging experience. And they can learn from this run and come back with their second run. And okay, now he's gonna test the dumping right there because he knows that he doesn't have time to get all the way back. So in the last 5 seconds, the CUNY robot is gonna go ahead and dump its load right there, and that is time. So let's give a big hand to the University of Colorado Boulder Not sure what happened to the robot. Hopefully we'll find out when we interview them. And also give a big hand to York